Hi, Physics 1. Mr. Janowski here, and this is the last part of the slides for chapters 2 and 3 before we get to the big quiz. So let's see what's going on. So what are parallel vectors? These are vectors that are either in the same direction or in exactly opposite directions. And those are fairly easy to add together. Question 2, if you have two vectors that aren't parallel, how can you add them together? The two ways we talked about are the parallelogram method and tip to tail. Question 3, who is Mr. Misconception? That would be Aristotle. He got a lot of things wrong, especially about physics. Question 4, if it disagrees with experiment, it's wrong. Richard Feynman taught us that. That is really the key to doing science. You have to always check your ideas against the universe through experiment or sometimes through observation. And if the universe tells you that you are wrong, then you are wrong. And that's all there is to it. Question 5. What experiment did Galileo perform to prove Aristotle wrong about forces and objects in motion? This was the thing with the ramps. So the ball goes down the ramp and speeds up because there's a net force in it, so its motion is changing. Then it goes across the flat part where there is no net force, and so its motion doesn't change. So what he's proving here, what Aristotle believed was that you need violent imposed motion to keep something moving. And what Galileo's experiment proved is that no, you don't need forces to keep things moving. If there's no net force on the ball, it'll just go straight line, constant speed. And finally, 6, what scientific principle does the tablecloth trick demonstrate? That would be Newton's first law of motion, also known as the law of inertia. So Newton's first law says that every object continues in a state of rest or of uniform speed in a straight line unless acted on by non-zero net force. So yeah, if it's at rest and there's no net force in it, it stays at rest. If it's already moving and there's no net force in it, it will have uniform speed in a straight line. Straight line, constant speed is how we usually say it in physics. So yeah, that's Newton's first law, which is exactly the same thing as the equilibrium rule that we learned earlier in this chapter. So that whenever the net force on an object is zero, the object is in mechanical equilibrium, which means that its motion, or lack thereof, isn't going to change. So put more simply, objects tend to keep doing whatever they were doing until there's a net force on them, and then their motion or lack of motion will change. So what is mass? Mass is a measure of inertia. So what is inertia? Inertia is laziness. Inertia is the resistance that an object exhibits in response to any effort made to start it, stop it, or otherwise change its state of motion. So, that idea. If the object will tend to keep doing what it was doing, and the measure of, well, how strongly does it tend to keep doing that, what it was doing, is its inertia, and the measure of inertia is mass. So in general, more mass equals more inertia equals more reluctance to changes in motion, which is demonstrated by this slide here. So we have Lionel Messi, and he's about to kick a soccer ball over here, and over here he's about to kick a bowling ball. Now, soccer balls and bowling balls are, the same shape. They have roughly the same volume. The thing that's really different about them is their mass. The bowling ball has much more mass than the soccer ball, which means the bowling ball has more inertia, which means it's more reluctant to change its motion. So that means when Leo puts the same amount of force on both of these objects, the motion of the bowling ball, or we're going to go from a lack of motion, the bowling ball would be at rest. Both of these things would be at rest at the beginning. So when Leo puts the same amount of force on both of them, the bowling ball's motion is not going to change as much. It's going to move, but it's not going to be as dramatic a change because the bowling ball has more mass, which is more inertia, which is more reluctance, which is more laziness. So misconceptions. The easier one, mass is not the same thing as volume. So both mass and volume are measures of how much stuff there is, but they measure different things about that. It's measuring how much stuff there is in very different ways. So mass is a measure of inertia. And the unit we like for mass in physics is the kilogram, kg. Volume is how much space an object occupies. And there are lots of different units for volume. Liters, cubic centimeters, these are common ones that we use in science. But also gallons, cups, teaspoons, things like that. The mass is not volume misconception is going to be the less common one at our age. But you can still get confused by this, but it's not as common as the next one. This next one always gives people trouble when they're starting to learn physics. So mass is not the same thing as weight. So again, mass is a measure of inertia, and it has units of kilograms, kg, and mass is also a scalar, which means mass has a magnitude, but it does not have a direction. Your mass does not have a direction. Weight, on the other hand, is a force, so it has units of newtons and also pounds. Pounds is a different unit for force. And your weight is a vector. It has a direction. Your weight is down towards the center of the Earth. So astronauts can experience weightlessness if they're up in orbit, but no one ever experiences masslessness. So, yeah, if you're in the International Space Station, you can lose all of your weight, but you cannot lose all of your mass, because if you lost all of your mass, you wouldn't be there. So, another thing that makes this so particularly challenging is that because we will spend our entire lives very near the surface of the Earth, where Earth's gravity is just very uniform, fairly uniform. It's not perfectly uniform, but it's pretty uniform across the whole surface of the Earth. So gravity is always pulling on us about equally strongly, which means we get in this habit, this sloppy physics habit, of just quickly converting from mass in kilograms to weight in pounds, or vice versa, weight in pounds to mass in kilograms. So if you ask, Google or whatever to do this conversion, it'll do it for you. But really, these are measuring different types of things. Again, kilograms are the units for mass, and pounds are the units for they're not our favorite units in physics, but they're units for force, and in this case, weight. So to demonstrate this, or an example of this, is that it would be easier to pick up a boulder on the moon because it would weigh less. So the gravity on the moon is about 1/6 that of Earth. So if you had a rock on Earth that weighed 120 pounds, it would be pretty difficult to lift that up. If you took that rock to the moon and tried to lift it up there, its weight would be 1/6 as much as what it was on Earth. So on Earth, it's 120 pounds. On the moon, it's only 20 pounds. So no difficulty at all picking that one up. So its weight would change. Its mass would stay the same. This rock has as much mass as it has. So if you were to, let me go back. When you're lifting something up, you are fighting against its weight, which is the Earth's pulling it downwards with the force due to gravity. So that will change depending on what planetary body you're standing on. If, on the other hand, you take this boulder and you start twisting side to side with it, so you're rapidly changing its motion. So you're stopped at one end and then moving it quickly to the other side, then slowing it down and stopping it, and then moving it back. Because you're changing its state of motion, its direction and its speed and all of that stuff, you keep changing that. What you're fighting against in that case is its mass. And its mass is the same, whether it's on the Earth or the moon. So that part would stay the same. So here's our slide. Our quantity is mass. Its symbol is m, which is wonderful. M for mass. That makes perfect sense. Again, I keep warning you, it won't always be that way. Eventually, we'll get to quantities whose symbols don't seem to be related to them. There's no way around that. Units, kilograms, lowercase k, lowercase g. And mass, again, is a scalar. Your mass does not have a direction. Your weight does. Your weight goes down, but your weight is a force. Your mass doesn't have a direction because it's a scalar. So back to this idea of inertia. So imagine that you are the passenger in a car traveling east at 50 miles per hour. The driver wants Chipotle for lunch, but you want Qdoba, so you flip a coin to decide. So when you flip this coin, why doesn't the coin hit you in the face at 50 miles per hour? And we're ignoring air resistance and wind and all that kind of thing. Excuse me, I hope that wasn't too loud. It's because the coin has inertia. The coin was already going down the road at 50 miles per hour. So when you flip it up, you're putting a force on it that changes its up and down motion. But you're not putting a force on it to change its east-west motion. So because this coin was already moving east at 50 miles per hour, and you put no force on it, east or west, that motion is not going to change. So it was already in motion in a straight line at a constant speed. You didn't apply an east or west force on it, so that motion doesn't change. And again, I pointed this out. This is just to preview something that will become important in later chapters. But up and down and east and west are perpendicular to each other. And that's a very useful thing in physics. When you have motion or other things that you can divide into perpendicular aspects, components is the word we're going to use later. It's very useful because when things are perpendicular, mathematically, we say that they are independent. Basically, they stay out of each other's way. So you flipping up on this coin does not affect its east and west motion because up is perpendicular to east and west. So the up-down force you apply stays out of the way of the east and west motion because they're perpendicular. And so then we get to this idea. So this is this very contrived situation that demonstrates something about physics. And I'll go through this kind of quickly. This is the one we broke up into little groups and discussed. So in this situation, we're completely ignoring air resistance. We do that a lot in physics. We're ignoring air resistance and wind. So what's going on here? Paul, the pitcher, is going to throw his 100-mile-per-hour fastball to the catcher. And behind the catcher is standing Alice, and Alice has a radar gun pointed at this pitch. And for some reason, this is the very contrived thing about this physical example, they're doing this on the back of a truck that is going east at 40 miles per hour down the road. And we're going to try to figure out, well, what does Alice's radar gun read? And at the same time, we have Billy just standing there in the middle of the road, and he's pointing his radar gun at the pitch. So he's measuring the speed of the pitch, not of the truck. And we're going to try to figure out, what does his radar gun read? And then finally, you have Charlie, who is quite recklessly standing on top of a car that's going west. So notice the car is going in the opposite direction as the truck. The car is going west at 50 miles per hour, and Charlie is going to try to measure the speed of the baseball with his radar gun. So we had to figure out, well, what does each scout's radar gun read? So first, Alice. Alice's radar gun is going to read 100 miles per hour because as far as she and her radar gun are concerned, they're at rest on the truck. They're going to say the truck isn't going east at 40 miles per hour. They're going to say, no, the truck is at rest. And it's actually the road that's going west at 40 miles per hour. Sounds weird, but stick with me on that one. So she says she and the radar gun are at rest. The catcher and Paul, the pitcher, they're at rest. So when he throws his 100 mile per hour fastball relative to the truck, that's exactly what the gun measures. So now on to Billy. So Billy's radar gun is going to measure 140 miles per hour. The reason being, Billy and his radar gun claim that they're at rest on the ground, and the ground is at rest, and the truck is going east at 40 miles per hour, and the pitch is going east at 100 miles per hour relative to the truck. So this radar gun is going to read that 40 plus that 100, and it's going to read 140. And finally, the tricky one, we get to Charlie. So Charlie's radar gun is going to measure 190 miles per hour. The reason being, Charlie and his radar gun and the car are all going to claim that they are at rest. Billy says, no, the car is going 50 miles an hour west. Charlie claims, no, me and the car and the radar gun are at rest, and the ground is going by at 50 miles an hour east. This is according to Charlie's point of view. So he says the ground's going by at 50, is going east at 50 miles per hour. The truck is going 40 miles per hour east relative to the ground, and the pitch is going 100 miles per hour east relative to the truck. So he's got to add all three of these up, and he comes up with 190 miles per hour. So the $1 million question is, which one of these people is correct? And the answer is, from a physics perspective, they are all correct because they all have their own frame of reference. And what a frame of reference is, it's as long as you're not accelerating, which we'll learn about acceleration next chapter, but none of these guys are changing their speed, and none of these guys are changing their direction. So they're not accelerating is what that means. So if you're in a frame of reference that is not accelerating, you can do your physics and make your measurements, and every measurement you come up with works as long as you stick to that frame of reference. So the person who figured out how you can add the velocity from one frame of reference to that of another frame of reference was Galileo. He figured all of this stuff out. And so this kind of thing we call a Galilean transformation. And so then we played the Kahoot. Well, next we broke up into groups and did that stuff. And then we played the Kahoot. And we didn't watch the Cassini video. That was very topical a few years ago when the class got to this. Cassini, it was a satellite going around Saturn, satellite probe. Yeah. And they intentionally destroyed it a few years ago. They sent it crashing into Saturn. And it was a glorious, fiery death. So if you're interested, go through the slides, get to that video. But yeah, that's it for these slides. Hopefully you found that helpful.